This is video 8 on employing the Medmon E300 corneal topographer's contact lens module. Let's open up a patient file, select a topography, click on Home, and then Contact Lens. When you first start out, select the manufacturers that are available from North America. You'll note the boxes presently checked are all the manufacturers available from North America that have put their contact lens designs into the Medmon. You can click OK. You won't have to open up this manufacturer's icon unless a new manufacturer has been added to a recent release of the software. Otherwise, you're just going to enter in the patient's RX if it isn't already entered in the patient file. So on the main window where you enter patient information, if you punch in your patient's spectacle RX, it automatically comes up in the contact lens design window. Next, let's select the specific lens we want to fit on this eye. Let's design for this patient a simple multi-curve that we could get from any lab in the world. Say OK. The software will then drop a theoretical contact lens on top of your patient's eye, and it will default the base curve generally very close to flat K. You will manipulate the contact lens parameters to produce the best possible fluorescein pattern. And we start by first determining visible iris diameter. And we click on Annotate and then Ruler and measure visible iris diameter. We're getting a close to 12 millimeter HVID. We'll select to delete that annotation, and you can do that by right-clicking and then deleting. Next, let's pick up the contact lens and place it somewhere near the geometric center. So ignore the placido and center the contact lens in relationship with the sclera. So looking at the white of the eye around here and placing your contact lens as it appears centered not to the placido rings that you can see just outside of the lens, but more so to the iris or limbus. Next, let's choose the lens diameter that we would prefer. In this case, we fit the patient with a 9.5 and apply. And click your cursor in the center and measure the tear film clearance, or TFC, along the right-hand side here. It's indicated to be 24 microns. For fluorescein to be seen by the human eye, it must be in excess of 20 microns. In other words, for us to see fluorescein behind our slit lamp, we must have a thickness of tear layer and density of fluorescein molecules somewhere in the neighborhood of 20 or more microns. If you want to see a nice even central fluorescein pattern on your actual fit, you must have a tear film clearance at the apex of at least 20 microns. With 24 microns, that would be comfortable. We're looking for somewhere between 20 to 25 on a normal eye. Next, take this white axis line and find the point on the graph where the lens seems to land on opposing sides. And it appears that on our with the rule corneal astigmat, this lens lands very close to 9 o'clock, and again on its opposing side at 3 o'clock. So we have apical clearance of approximately 24 microns down to touch at 9 o'clock. You see the dotted section of the line here corresponding with the dotted section on the graph. Solid section of the line here corresponding solid section there. So we have our 24 microns apical clearance. Heading down to 3 o'clock, we have our touch, and then our edge lift, our apical clearance toward 9 o'clock with our edge lift. So this is an ideal relationship to keep the lens on lateral center. Then we take our axis line and drag it to the vertical meridian, and we can see that this patient has a fair amount of tear layer clearance heading toward 12 and heading toward 6 o'clock. Dotted section of the line here corresponding with the dotted section of the line here, solid section of the line there corresponding with solid section here. If we click our cursor at the edge of the inner pink circle, which is the optic zone junction, we're showing 41 microns heading north and 85 microns heading south or inferior. This is a significant amount of inferior clearance and would likely cause the lens to tilt and rock across the vertical meridian because there is excessive lift of the lens at 12 and 6 o'clock. This is a floor seam pattern of the actual lens on eye designed from our Medmon, and you can see that this contact lens has an acceptable level of apical clearance. Floor seam can just be seen under the center of the contact lens, so this is good. We have landing at 9 o'clock and landing at 3 o'clock with a healthy edge lift on both sides. The problem, however, is the significant inferior lift and superior lift that's causing the lens to tilt and also ride high. This patient needs a toric GP lens. So let's go back to our contact lens and try to better design it from our Medmon software. Click on Display to bring up the Edit box again and select Toric. Now we create two meridians of curvature and apply that. The same rules apply to the toric contact lens. We want to create a lens that lands at 3 and 9 o'clock and lifts at 12 and 6 o'clock. Presently, our contact lens is not landing across the horizontal meridian. The horizontal meridian you can also see is our flat meridian by that blue line. So let's steepen the base curve along the flat meridian by a half diopter step. On the vertical meridian, we appear to be very near to bearing or definite bearing at 12 and 6. We want our contact lens to lift so it can freely move with each blink and create a good tear pump. So let's flatten the lens across the steep meridian so that our contact lens will be able to move with each blink. And click Apply. Now we have a lens that lands at 3 and 9 o'clock, and along the vertical meridian it lifts at 12 and 6 o'clock. This would be ideal for a good RGP fit. The last thing that one might do is adjust the optic zone size to soften its peripheral landing. Notice this narrow point of bearing and a very steep angle as the lens comes back toward the cornea and touches. Let's increase the peripheral curve width, reduce the optic zone size slightly, and see what that does to those points of bearing. When we apply, notice how you shallow out how that lens comes back toward the cornea and creates a much wider, softer area of bearing. Now here's the actual lens that was fit by these same parameters. And you notice you've got virtually 360 degrees of alignment, but appears to be a very thin channel at 12 and 6 o'clock, which would allow the lens to freely move with each blink. So the tear film definitely shows what appears to be bearing at 3 and 9 o'clock, and then that bearing thins out throughout 12 and 6 o'clock to allow for the lens to freely move in the vertical meridian. And we also have much better centration than we had with the spherical GP lens. This concludes the section on using the contact lens module in your Medmon E300 corneal topographer.